Now, the rest of the main group topic is going to be talking about compounds, and we're going to start off with oxides, and there's going to be many movies associated with oxides, but I thought it would be worthwhile here, before we got specific about the oxides of different elements, just to talk about them in general. And one of the ways we can talk about in general is looking at the bonding. Bonding can be ionic. So in other words, you have a metal cation and then O2 minus usually, although there are some other exceptions, as the anion. And so of course alkaline metals, just about everything they do is ionic. Here's an example of what lithium oxide looks like. So the red balls are oxygens. They crystallize in a face-centered cubic cell. Now if you think of what you know about face-centered, you've got an atom on each corner. Well, each atom on the corner is shared with 7 other unit cells, so each of these is worth an eighth of an atom. As you have 8 of them, the fact that you have oxygens on the corners is worth 1 oxygen. Then you have an oxygen on each of the 6 faces. Each face is just shared with 1 other unit cell, so each of these oxygens is worth half an oxygen to the particular unit cell. So you've got total of 6 of those, so that's a total of 3 oxygens. So in this unit cell, there's the equivalent of 4 oxygens. The greenies are the lithium atoms. They look like they make a cube. Those are actually inside the unit cell, formed by the oxygens. So each of these green circles represents a whole lithium. So you've got 8 lithiums to 4 oxygens, Li2O, as you would expect. So the alkaline metals all form ionic oxides, as I hope you would predict. The alkaline earth metals also form them, as do these other metal atoms. So aluminium, gallium, thallium, lead oxide and bismuth oxide should all be thought of as being ionic oxides. Now something should leap out at you, smack you in the face, and that is that there is a metal that is not an oxide. And don't talk about these radioactive ones, because we don't talk about the radioactive ones, and that is tin. Tin's oxide actually is much better described as being network covalent, and of course this is a type of bonding with which you should be familiar. Boron, silicon, germanium, arsenic, antimony and tellurium, in other words all the metalloids by and large, form network covalent oxide bonding. Nice example of that, silicon dioxide, which forms this nice little pretty picture, octahedral silicons bridged by oxygen atoms. Okay, so this is the form of silicon dioxide, the main form of silicon dioxide with which you should be familiar. Again, in the same way that tin was sort of the odd one out, bridging between the metals and the non-metals, and selenium as a non-metal, something pretty much a non-metal all the time, forms a network covalent oxide. And of course the remaining non-metal atoms all form molecular covalent. In other words, you can have distinct molecules of their oxides, so carbon, nitrogen, oxygen, fluorine. So obviously CO2 and O2, for example. O2's oxide is molecular. OF2, fairly famous one. Phosphorus, P4O10, P2O3, P2O5, and so on, SO2, SO3. Lots and lots of fun chlorine oxides, ClO2 probably being the most famous one. Bromine oxide, rather unstable. We'll talk about all these, of course, in more detail. Iodine oxide is molecular and it's strange. And xenon forms, of course, some oxides, molecular oxides, being part of that really fascinating chemistry of xenon that we'll explore a bit later on as well. Hydrogen, of course, has a molecular oxide, H2O or H2O2. And so here's some examples of those oxides. Okay, so bonding in oxides is going to be one of the fundamental categorizations that we'll explore when we talk about the oxides of elements in more detail in separate movies. Probably going to notice, I don't know how well you notice when I sort of stopped the recording and started again, but anyway, I was going full flow on this particular slide, and then my phone started going off, because at 5:08 I have an alarm set every day to remind me to take a little pill, and also when I'm at work to remind me that my bus, which leaves at 5:28, is 20 minutes away, so I should start wrapping up what I'm doing. So anyway, the previous slide had this wonderful chiming bell tower sound that actually made it through this microphone. So here we go again. Talking about oxides, continuing to talk about oxides in A-level. you talked about whether they were basic or acidic, and it is definitely worth discussing that as a further categorization of oxide behavior. So let's consider lithium for starters, right? Notice I've got it in blue because blue means basic, and when I talk about its reactions, I'm doing it with a blue background and using blue type for the lithium oxide. In other words, lithium oxide is basic because when it reacts with HCl, you get this reaction which you should recognize, whatever, one of those rewords, as being a neutralization. Acid plus base gives us a salt plus water. Lithium oxide is basic. If you take lithium oxide, try reacting up with a base, you do not get a neutralization reaction. And just like lithium, all its friends within the alkaline metal group have basic oxides. The alkaline earths have basic oxides. Thallium gives us a basic oxide. Okay, notice some of those metals are not there. The metals that are closer to the metalloid demarcation: aluminium, gallium, indium, tin, and interesting lead and bismuth. I haven't put those in blue yet. Let's put some red on this, shall we? Nitrogen, right, has a very acidic oxide. If we take, for example, N2O3, again writing it in red for oxide with a red for acid, with a red background for acid, you take N2O3 reacted up with HCl, you do not get a neutralization. However, if you take it with sodium hydroxide, you make water and sodium nitrite. So again, acid plus base gives us a salt plus water. N2O3 and all nitrogen oxides are acidic. And if we fill up the rest of the non-metals there, at least those particular non-metals, they all give us these acidic oxides. Okay. Also, some metalloids, boron, silicon, and tellurium, have acidic oxides. Some might argue, you can find people who say boron can be amphoteric, silicon can be amphoteric. I'm not going to go with that, right? Those are acidic oxides. Okay. Now, of course, if it's not acidic, it's not basic, it's neutral, right? Not in this case. If it's not acidic or basic, it's both. It's amphoteric, and aluminium is the one from A level that is emphasized here. You take aluminium oxide and you write it as a blue for base, react it with acid, and again you get the very distinctive salt plus water, aluminum chloride plus water. You take it, react it up with a base, so aluminum oxide plus base. Within water you get this sodium aluminate, I don't know. This thing here doesn't actually look like that's aluminium oxide acting as an acid because you don't get that salt plus water, but it's very definitely acting as a Lewis acid there. Other amphoteric oxides: gallium, indium, tin, and lead, all other metals that have amphoteric oxides. Beryllium has an amphoteric oxide, and this is an example of that nice diagonal stuff that I'm going to keep referring to. A lot of times beryllium and aluminium do the same things. You'll see in other cases lithium and magnesium are kind of weird in the same way. Okay, beryllium, the diagonal relationships very important between lithium and magnesium, between beryllium and aluminium. Germanium, also amphoteric. And hydrogen oxide, amphoteric, except of course you're used to saying that hydrogen oxide is amphiprotic, but very definitely amphoteric. It can act as an acid or a base. And you'll notice I've left a few unshaded. That's because these three can be acidic or amphoteric. Essentially the lower oxidation state of these ones, so AS2O3, Sp2O3, Bi2O3, is going to be amphoteric, but the higher oxidation states, so the oxidation state of 5, so AS2O5, Sp2O5, and Bi2O5 is going to be acidic. Okay, so we can continue talking, and we will continue talking about oxides as being basic, amphoteric, or acidic. Also worthwhile, and indeed a lot of A-levels emphasize it from this perspective, talking about oxides in water to make hydroxides. Okay, and if we think about all of these hydroxides, you've got your element, whatever it is, bonded to an O, bonded to an H. If we think about lithium hydroxide, which we make with lithium oxide in water, we make this lithium hydroxide here. What does lithium hydroxide do in water? It dissociates by breaking the XO, the lithium O bond, giving us lithium cations and OH minus anions, very, very distinctly basic. Conversely, of course, if we take a nitrogen oxide, in this case I'm going to do N2O5 because I like it more, react that up with water, then we make nitric acid. If you remember the formula of nitric acid, it's that there. Put nitric acid in water, we get H plus and NO3 minus, so it's breaking that OH bond here. So when it's a basic oxide in water, you get this bond's going to be broken, right, the one between the element and the oxygen. When it's an acidic oxide in water making the hydroxide, you break the bond between the O and the H. Just going to throw in very, very quickly some other acidic oxides, right, to what happens in water. So CO2 in water gives you carbonic acid. There's the structure there. Again, you can see the O and the H. This is what breaks when it acts as an acid. Another nitrogen, N2O3, gives you nitrous acid, giving you H plus and nitrite there. Two phosphorus ones, most common phosphorus oxides, P2O3, P2O5 in water, give you respectively phosphorus acid and phosphoric acid. Two sulfurs give you in water respectively sulfurous acid. There's one way to write the structure there, again emphasizing you've got these OHs, they are these hydroxides, except they're not really hydroxides because the bond breaks between the O and the H. And of course SO3 gives us sulfuric acid. Both of these should be very familiar with you from the old acid rain studies that you did before. Chlorine, a couple of chlorines there, could have gone with other ones, but I chose ones that give us chloric acid and perchloric acid, and that's the structure of those. So anyway, there's multiple movies associated with the oxides, with the hydroxides, with the oxygen containing anions of main group elements that you will need to watch. But here we've gone through some of the significant overall trends.